Okay, let me take another run at this. I just started the video and I screwed up something pretty much immediately. Let's see if it goes a little better this time. Okay, let's do these rational functions. There's 15 of these. I'll try to run through all 15. Even though we already did the first few. That's fine. Let's go. So the first thing we're supposed to do here is completely factor the function. But this one happens to already be completely factored. It's a constant over a linear. There's literally nothing we can do. But still, I would recommend that every single time you're trying to graph a rational function, you do all of these things here that I'm shaking back and forth. You want to find the function's completely factored form, and then you want to find all these properties. You want to find any asymptotes, you want to find coordinates of any holes, you want to find the x and y intercepts, and even you want to do a little more than that too. We'll cross that bridge when we come to it. But looking here, my factored form would, I guess it would just be the function in the form it's in right now. We don't have to do anything. That's way too thick. For asymptotes, we know that our vertical asymptotes are the zeros of the denominator that are not also zeros of the numerator. So for us, that means the only zero in our denominator is 3. And the numerator has no zeros, so obviously this will be a vertical asymptote. The fact that there are no values of x that are zeros of the denominator and numerator tells me right away that there are no holes. Because that's how you get a hole, is when there's a value of x that is a zero of both the numerator and denominator. So maybe let's fill both of those in. To find the horizontal asymptote, we want to use that rule about the degree of the numerator and denominator. So given that a rational function is always the quotient of two polynomial functions, like f of x and g of x, the horizontal asymptote is always about, you look at the degree of f, and if it's greater than g, something happens. You look at the degree of f, and if it's less than function g, something happens. And if f and g have the same degree, something else happens. We could review those rules. Let's do that real fast. When f has the greater degree, that's when, we often call that a function that is top heavy. And when this happens, you have no horizontal asymptote, but you might have a more complicated end behavior asymptote, like an oblique asymptote, or an asymptote that's actually in the shape of like a parabola or a cubic function or some greater polynomial than that. But that's what happens when the numerator has the greater degree. When the denominator has the greater degree, your asymptote is just always 0. And that's what we have now. So we can say pretty safely that our horizontal asymptote is at y equals 0. And remember I mentioned in class, I'm putting these s's here to imply that maybe there's a second horizontal asymptote, but there literally can never be. So I'm kind of just being a jerk when I do that, honestly. So just remember, there will never ever be more than one horizontal asymptote. Also, if you determine that there is a horizontal asymptote, then there will never ever be a slant asymptote too. You could never have both, because these are our end behavior asymptotes, and there can only ever be one end behavior asymptote. Now the vertical asymptotes, there can be more than one, and blah blah blah. Vertical asymptotes are not end behavior asymptotes, so they're different. Okay, where am I? The intercepts now. The x-intercepts, again, if I'm on the x-axis somewhere, then I'm a point where the y-coordinate is 0. And you got to solve for the x-coordinate. Okay, but the x-intercepts are always going to be the zeros of the numerator that don't cancel out, because again, the ones that cancel out become holes. But if the numerator ever equals 0, then the whole function equals 0, and that'll be your x-intercept. And again, our numerator is a constant, so it doesn't equal 0, so I'm expecting this graph to have no x-intercepts. So what about y-intercepts? Well, again, if I'm a y-intercept, and I'm here on the y-axis, then I know for a fact that my x-coordinate is 0, and I'd have to figure out my y. But that's exactly what functions are for. Just take the function and figure out what f of 0 is. When you plug 0 in, you get 1 over 0 minus 3, which is 1 over negative 3, which implies that our y-intercept is at 0, 1 third, negative a third. Remember to give your x and y-intercepts as ordered pairs. Don't just give the one value. Give it as an ordered pair. Alright, so now cleaning all this up. Now that I've gathered all this info, I should be able to sketch the graph pretty easily. So in red, I'll plot my asymptotes. We have one at 3. So just draw it as a dashed line. Our other asymptote is a horizontal asymptote at 0, so draw that. And then plot the only other thing we have, which is our y-intercept, which is at 0, -1/3. So that would be like here. Oh, I want that to be any color other than red, I think. So how about right there? Okay, well now, I think we talked in class about how you sort of want to like test intervals now. So like, for example, the intervals that I'm talking about are, there's an interval to the left of the asymptote. And when I say sort of test this interval, you just plug in any number that's less than the coordinate of the asymptote, so any number less than 3, and you just evaluate, because what you want to do is just figure out, am I below the horizontal asymptote or above it? Now I don't have to do a test point for this interval because we have the y-intercept, and we can see that we're below. And that tells me then that the entire branch of this rational function is going to be below and just have that sort of hyperbolic shape. Now obviously this was not smooth at all. We must hit this point and continue sort of deeper in before we turn and come down. Again, you guys know that this shape does matter to me, and I do want you to be a little more careful about shaping these things well. But that's it. There's our branch. Now technically though, the next sort of interval is over here. Let's do it in green. But now over here, we want to figure out where does our next branch live, and it could technically live below the asymptote. So you'd want to run a second test value, something bigger than 3, to see if you're positive or negative. If you get a value that's negative, then your second branch would live entirely underneath. If you get a value that's positive, you'll live above. And I did mention in class that it's not possible for us to be below and then below again. Not for a function this simple. If we were going to ever be below and then below again, you'd have more complicated polynomials here, like a quadratic over a cubic or something, then maybe it's possible. But for a simple linear over a linear or a constant over a linear, these things are going to behave pretty normally. You're going to have one below and then one above, or one above and then one below. Okay, anyway, I'm blabbing. Let's run our test point. 4 is sort of the obvious choice, but you could test 6 or 7 or 8, anything as long as it's bigger than 3. So let's test. Let's go f of 4. I'm getting 1/4 minus 3. That's 1. So I know that the point 4, 1 is on my graph. And that means I can sketch the next branch of this function, and it goes da 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 da. Okay, that was really not good enough. We're going to come down and hit that point, turn, be asymptotic. But that's it. There's your graph. I'll take this away now. I don't really need that anymore. But there's your graph. I should see the asymptotes and I should see the shape of the function. Moving on. I'm going to go faster this time. All right. So for this function, we see that there is actually a lot of factoring for us to do. In the numerator, we can factor out a GCF of 3 to get 3 times x plus 2. In the denominator, we have a quadratic that's factorable. We would get x plus 1 and x plus 2. So this is a much more interesting function because this time we do have a factor that cancels, which means my final factored form would be the 3 over x plus 1. But with a domain restriction of x cannot be the -2. So now that I've got that factored form, I can go back and attack all of these things, right? Let's go back and find all of these properties. So we just said that our factored form is the x over x plus, or 3 over x plus 1, sorry, with the domain restriction. Then we can do our asymptotes. We see that the only vertical asymptote is actually at -1. And we see that this time we did have a factor that cancels from the x plus 2. That implies that we're gonna actually have a hole, and it'll be at a point whose x coordinate is -2. And since you do have to give these holes as coordinates, you have to know how to find the y value. And to find the y value, I mean, normally you would just plug x into the function and evaluate, but this function will be undefined at -2. That's the whole nature of a hole, right? Is holes occur when the function is undefined. So if I plug into the original function, I'll get division by 0. I'll be undefined. If I plug into this orange factored version, then I would still get division by 0 and be undefined. But if I plug into the green version, where I've actually canceled out the factor of x plus 2, then I can evaluate this and get a real output. So if I take the 3 over -2 plus 1, then I get 3 over -1, which is -3. And so that tells me that the y-coordinate of my hole is -3. So I got that. Now for the horizontal asymptote, there can only ever be one. I've got that bottom-heavy structure again, where I'll just automatically have a horizontal asymptote at y equals 0, which means that I do not have a slant asymptote, so that is none. For an x-intercept, this one's a little tricky, because if you look at the original equation, you might say that there is an x-intercept because -2 would be a 0. So you might be tempted to say that there's an x-intercept at -2. But remember that that -2 was a 0 of both the top and the bottom. It canceled out. So it's actually a hole for us, and it's not an x-intercept. And since our simplified version over here, our numerator has no zeros, so you should be expecting none. The one thing that was a 0 turned out to be a hole, not an x-intercept. For the y-intercepts, we said we're just going to plug in 0. And I would still say the easiest place to plug in 0 to evaluate, I mean, the green version is probably the easiest place. But even if you hadn't factored yet, you could plug into the original unfactored version, because you know that 0 will kill off this whole term. 0 will kill off this term. 0 will kill off this term. And your y-intercept is always just going to be the quotient of those two constants on the end. It's going to be 6 over 2, which is 3. So we know that we have a y-intercept at 0, 3. All right, let's get plotting. We just said we have a vertical asymptote at -1, so you show that. We said that we have a hole at -2, -3. And again, make sure you draw that pretty big for me so that I can see it. We have a point 0, 3. So draw that nice and solid. And that's it. That's all we've got. And it turns out that's all we need anyway, because, you know, if you look at sort of thing 4 up here where it says sketch, making sure to label a point in each region. Remember that when we talk about region, we're talking about, we're just talking about the intervals that lie between the asymptotes, the vertical asymptotes, I should say. So there would be an interval to the left of the asymptote, and there'd be a second interval to the right. I'm doing this wrong. To the right. Okay, so anyway, if I make that a little see-through, if I make this a little bit see-through, then we would always want to run a test point in each of these regions. So in the red zone over here, I've already got my test point because we had a hole. So that hole works as a test point for us. Ooh, I never drew the horizontal asymptote. The horizontal asymptote is here at 0. So between an asymptote that shapes us and between having a point that we know, you know, it basically counts as a point even though it's a hole, but we know we've got to be horizontally asymptotic here. We've got to hit this point. Then we've got to be vertically asymptotic here. So we've got our shape nailed down. And same thing with the red region over here. We don't need to run a test point because we have our y-intercept. So I'm just going to come screaming down this vertical asymptote, hit this y-intercept, continue, curve out, and go here. That's it. This is another simple one. Let's move on to 3. Okay, 3. 3 wants to be factored, kind of. I can't do anything in the numerator. That's going to just stay x cubed. My denominator, though, is a difference of squares, so I can factor that down to x plus 2 and x minus 2. So this should feel a lot different from the previous one, because right away we can see this graph's going to have 2 vertical asymptotes. It's going to have one at -2 and one at +2. And right away that tells me that in the previous problem, remember we were only considering two regions, the red region, which by the way, let me just borrow that. My mouse is not working well. We would still have a region. We would care about all the stuff left of -2. My graph's going to have some shape over there. Then there's this guy. We need another region. We would need to care about what's happening to the right of +2, but there's a third region now that we also care about. Let's make it orange, I suppose. I need to actually care about what's happening in between 2. So I now have 3 different intervals in which I need to sort of run some test points. So again, we'll cross that bridge when we come to it, but for right now, hopefully that makes sense to you guys. When we talk about plot a point in each region, this is what we talk about. And actually there's going to be more, so hold on to your hats. So what's the deal? I've not really written anything down yet, so here's my little list of stuff. My factored form, I already did that. I'm not going to do that again. It's right there. You can see it. For vertical asymptote or asymptotes, this time the plural kicks in, and we actually have one at -2. And we have another one at x equals +2. For horizontal asymptote, all right, we have another big giant difference because we know that for our horizontal asymptote, we don't have one. You should be expecting that because the numerator has the greater degree, that this is going to be a time that we have a different kind of end behavior asymptote. And because the numerator is greater by 1, I do know that that end behavior asymptote will be linear. And I need to now go find its equation. So I need to grab this function here. And I need to do polynomial long division on it. So let's do that. Way down here where we have plenty of room. Where'd you go, buddy? Okay, let's do it. So when you're doing polynomial long division, you take the denominator and you divide it into the numerator. And I would advise that if you're missing a term, we go straight from x squared to a constant, you should include a term as sort of a placeholder for the missing terms. Even for this x cubed, and this is going to turn out to be not super important, but for others it might be very important. So let's go 0x squared and 0x's plus 0. Just now I have everything, a little more well-defined and easy to see. So what do we do now? We would ask ourselves, how many times does x squared divide into x cubed? So literally you're just doing x cubed divided by x squared. You get a quotient of x. So that means this quadratic goes into this cubic x times. So I would now find my x column, put the x in, and then the next step is to take that x and distribute it through. So I would get x cubed, then I would get 0x squareds, then I would get minus 4x. Be right back. Okay, I'm back. So where were we? We were polynomial long dividing. So what's the next step? Once you've found how many times your function divides into your other function, you multiply that through, and now we are subtracting. So be really careful with your subtraction. The first two terms should always cancel out. It just so happens that these guys that I told you to put in as placeholders, they do end up being irrelevant this time. But here, I don't know, it's kind of nice to see that you're doing 0 minus -4. Without this placeholder, you might have just kind of brought the -4 down. But if you have the 0, you might remember that you're doing 0 minus -4. So it needs to come back as a positive 4x. Now technically I should take this thing, drop it down, it would become sort of 4x plus 0, and you would divide again. But this is the exact point where I know that I can stop. I now have a remainder whose degree is less than the degree of my divisor. So that's the point where I stop, and I know that whatever I got down here, this is now my remainder. That's my remainder. This thing up here is my quotient. And of course this thing over here that I divided by, that's my divisor. And so that gives us sort of a third form of our function. We've got the given form of the function, which is sort of like the expanded form of the function, x squared minus 4. We know that we want to factor it, so factored form is our second form, x cubed over x plus 2x minus 2. And the third form that we are often going to want to consider is this form where we re-express the function as the quotient plus the remainder over the divisor, which means for this problem it's going to be the quotient is just x plus the remainder is the 4x divided by the divisor, the x squared minus 4. So this form holds some useful information for us because the quotient right here, that's the equation of the slant asymptote. So in this case our slant asymptote is y equals x. Okay, so that means we can go add that to our list of things that we now know. We now know that we have a slant asymptote and that its equation is y equals x, which means we can add that to our graph, because if our equation is y equals x, sometimes people forget this, but this is just an mx plus b deal. So if you just have x, then we're talking about 1x plus 0, right? So that means you've got a y-intercept of 0, you've got a slope of 1, so you're rising 1, running 1. So you can sketch the slant asymptote pretty easily. You just sketch it the same way you sketched every other line back in Algebra 1. So this thing is going to just go da 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 from corner to corner, running through all these squares. But there's my slant asymptote. Okay, do I have any holes? No. I don't have holes because there are no zeros of the numerator that are also zeros of the denominator. Do I have any x-intercepts? Yes, because the x-intercepts, remember, were the zeros of the numerator, and there is a zero of the numerator. It's 0. So there's an x-intercept at x equals 0, and plugging in 0 gives 0. So we know we pass through the origin. Are there any y-intercepts? Well, the y-intercepts occur at what you get when you plug in 0. So I actually just did this wrong. Yeah, sort of. Whatever. But it's 0, 0. So the x and y intercept are the same point. They're both 0, 0. Now something else just happened too that you probably picked up on. But this question of, hey, does the function cross its end behavior asymptote? Well, we just saw that we do have an x-intercept at 0, 0. And so if I plot a point at 0, 0, you can see that that does mean the graph is crossing its slant asymptote, okay? Because we actually can see that we pass right through it. So does the function cross its EBA? Yes. If it does cross, then where? Well, it crosses at the origin. It crosses at 0, 0. So you'd give me the coordinates of that point. Do we ever cross the slant asymptote again? Well, I think I told you in class that the way that you would answer this question is you'd grab the whole function and set the function equal to the equation of the slant asymptote. So you'd go x cubed over x squared minus 4. You'd set it equal to the equation of the slant asymptote, which is x, and then you try to solve this equation. So to solve this equation, you could imagine cross multiplying, or you could just imagine multiplying through by the x squared minus 4. If I multiply through by x squared minus 4, then on this side it cancels and I just get the x cubed. And over here the x distributes in and you get x cubed minus 4x. And then what will often happen is this term with the highest degree, that actually just cancels out for us when I subtract it from both sides. So I have 0 equals negative 4x. So I divide by negative 4 and I get 0 equals x. And so now because this equation, the equation where I took f of x and set it equal to the slant asymptote, because that solution, or because that equation actually has real solutions, we know that we do cross. Now, since we only have the one solution, we know that we only cross once. It's not like we come down, dip below the slant asymptote, and then turn and come back up through it, because we know that we only cross it once. So this orange region just got a little more interesting, and it turns out that this orange region needs to be two separate regions, because I need to consider what the function's doing to the left of that point of intersection and consider what it's doing to the right. So I need a whole other region now that I guess should be yellow. Are these colors different enough? I don't know. But we now have three regions that we should be testing, so let's just test them. So I don't know. Let's just run a t-chart, x and f of x. And then let's pick values from each region. So I need a value from the left of this asymptote, so -3 seems to work fine. I need somebody between these asymptotes and this x-intercept, so -1 is the obvious choice. On the other side, +1 is the obvious choice. And then something to the right of 2, I could pick 3 or 4 or 5, whatever. Let's just pick 3. Okay, so plugging in -3. The best place to plug these in, I would say, is probably the factored form. And so plugging into the factored form, -3 cubed is giving me -27. The denominator is giving me what? -1 times -5, so +5. So this is -5.4, because it's 5 2/5, so 5.4. Okay, great. Lovely. Is that helpful? I guess it is. Although the question is, at -3, is -5, is that actually below the asymptote or above it? It's not really helpful unless I actually know the value of the slant asymptote. So actually, in the case of a slant asymptote, you have a little more work to do. Luckily, in this case, it's easy, because our slant asymptote is y equals x. So we know that at -3, the actual asymptote is -3. So -5.4 is certainly below that. So we know that the entire branch, this is 5.4. So that tells me that the entire branch in the red region must be asymptotic here, following this end behavior asymptote. And then I would probably come up above, turn, and come back down through that point. But there's the rough shape in the red region. And I assume the shape in the green region would be largely the same, but it would, instead of being below, it would probably be above. But that's what we run test points for. Let's find out. At +3, the asymptote is 3. So if I plug in 3 and get a value less than 3, then my branch lives entirely below these asymptotes. But if I plug in 3 and get a value greater than 3, then I would live entirely above. And if I plug in 3, I'm going to get the same thing I got over here, but I'm going to get positive. So plugging in 3 gives me 3 cubed for 27. And in the denominator, I get 5 times 1, which is 5. So you can see we do again get exactly the same value of 5.4, but it's positive 5.4, so I am, in fact, above. So I do expect my graph to come down the vertical asymptote, hit that point, probably continue just a little bit further down, and then turn and go back up, 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 up along the slant asymptote. So there's 2 of my branches. Now what's happening in the middle? We'll run your test points again. -1 cubed is going to give -1. And -1 in the denominator is going to give +1 times -3, which is -3. So I'm getting -1/3 at -1. And again, the asymptote is at -1, and so obviously +1/3 is going to be above that. We're going to be here. And in all honesty, we shouldn't actually have to do a test point in the yellow region now, because if I'm coming down this asymptote, hitting that point, then hitting my x-intercept, I can't turn and come back up, because if I did, I'd have to cross the asymptote again, which I know I can't do. So I know that I must actually hit here and then just continue back down like that. And this will be the shape of our graph. But, you know, I've already I've already, you know, labeled the thing, so why don't we go ahead and just evaluate anyway. So plugging in 1 gives me 1 over 3 times negative 1. And 1 over 3 times negative 1 is negative a third, which I totally expected because we already knew that we were supposed to be negative. So the only thing I don't like is my graph is a little too steep. I should have come through here a little more flat and then come down. But whatever. There's my graph. How many minutes did that take? This is already a 30-minute video. We're on number 3. So these are taking a long time. But these, of course, will start to go faster once you understand all the steps. So let's try 4. All right. Step 1, as usual, is going to be to factor. So let's just pull this out right now. We know the first thing to do is find our factored form. The numerator is not factorable, so just bring that down, x squared. The denominator looks factorable to me. It's probably an x plus 3 and an x minus 2. Gotta go get my dog. Okay, I'm back. So we factored. From our factored form, we get a lot of information. We know that the 2 zeros of the denominator are going to be asymptotes. So we have an asymptote at negative 3, we have an asymptote at positive 2. We know that since the degrees are the same, we're going to use that rule that says that the horizontal asymptote is at y equals a over b, where a and b are those leading coefficients. So it's going to be 1. So this time our horizontal asymptote is at 1. And our 2 vertical asymptotes are at negative 3, so right here. And positive 2, so right here. Great. We know that since the 2 degrees were equal, we will not have a slant asymptote, none. We know that since none of these factors are shared factors between the top and bottom, that we won't have any holes. We know that since the numerator does have a 0, and it's 0, then that's going to be our x-intercept. And don't give it as x equals 0, that was wrong. Give it as an ordered pair. So the x-intercept is going to be at x equals 0. And the y value, when you plug in 0, you get 0. So again, it's the origin. And when you get the origin as your x-intercept, that means the origin is also your y-intercept. And then nothing else. So that's about it. So what other question am I supposed to consider before I start putting pen to paper? Don't forget, you're supposed to check and see if the function crosses its end behavior asymptote. And so to check that, you're going to grab the whole function. You're going to just grab all of f of x. And you're going to set it equal to whatever the equation of the end behavior asymptote is. For us, that's a horizontal asymptote. And for us, that is just 1. So we're just going to go x squared over x squared plus x minus 6. Just set that equal to 1. So now essentially you're cross multiplying. So you get x squared equals x squared plus x minus 6. Immediately you can just subtract x squared from both sides to get that to cancel. So you now have 0 equals x minus 6. So then you add 6. And because we do have a solution here of 6, do we cross? Yes, we do. And if so, where? We cross at a point whose x-coordinate is 6. To find the y-coordinate, you could take the 6 and plug it back in, but I hope it's pretty obvious that if we're crossing the horizontal asymptote whose equation is y equals 1, I think it's probably a safe bet that it's 1. The y-coordinate is 1, right? So let's start plotting stuff. At 6, 1, we're going to cross this here horizontal asymptote. Good news is we don't cross anywhere else. So I can plot my x-intercept at 0. And I can now rest assured that in my intervals, my little regions, let me just borrow these guys again. I have three regions I care about. The first region I care about is the region between those asymptotes, so this orange region. I have the region to the left of that asymptote, and I have the region to the right of the other asymptote. And I guess I did say that technically I'm supposed to care about this x-intercept, and so maybe actually I do need this guy too. Because maybe I am supposed to care about what's happening. Paste. Alright, so here's the deal. I don't really need to give a darn about what's happening to the left and right of this point, because I know that I cannot cross the horizontal asymptote here. The only place where I crossed the horizontal asymptote was over here at 6. So it's not actually possible for the graph to come up this asymptote, hit here, and then continue up and out. Because if it continued up and out, it would have to hit the asymptote somewhere, which we know it does not do, because the only place where it hits is at 6. So without running test points, I actually should be able to rest assured that because I have a point below the horizontal asymptote, this entire branch in this region should stay below the asymptote. So we should get this rough shape. Now, I don't know what's happening over here in the yellow zone. Am I below again, or am I above now? Well, for that, you better run a test point. So let's pick an x. Let's evaluate some f of x's. I need something less than -3, so let's test -5. And again, I would test my factored form. So -5 squared is a positive 25. -5 plus 3 is -2. And -5 minus 2 is -7, which means I'm looking at a 25 over positive 14. But again, all I really care about is, am I above or below this asymptote? And this asymptote is 1. So 25 over 14 is definitely greater than 1. But it's not quite 2. So at -5, I'll plot a point at 1. But not quite 2, somewhere in between. Doesn't have to be perfect. But I know there's a point right there. And that 1 point tells me that my graph must live entirely above this asymptote, hit there, continue up and out. And now I'm worried about what's happening over here, and guess what? I do need another region, because I do have to kind of worry about what's happening to the left of here and what's happening to the right of there. So really, I should be picking 2. Or should I? Maybe I don't need to. Because maybe once I know, if I run a test point at 4, let's do that. But as soon as I test 4, I plug in 4. I get 16 over 7 times 2. So 14 again. So I'm getting 16 over 14, which is, guess what? A little bit bigger than 1. So I am above. So that definitely tells me that in the green zone, I must be coming down this asymptote. I must hit here. Then I must hit at 6, passing down under this slant asymptote. And I'm not going to head down to infinity. That's not how this works. I have to continue just being asymptotic. So I don't really need to run another test point over here. I know that what's going to happen is simply oh, rats. Dum-dum. Okay, go away. Alright, what's going to happen is I'm going to dip below the asymptote, but then as I go to infinity, I have to approach the asymptote. So I'll dip down below the asymptote, but I'll eventually turn and come back up and be asymptotic from underneath. Now this graph's wonky as heck. It's pretty hard to show all this stuff without more room. But I do want to smooth this out because this is not looking good enough to me. So let's try to smooth that out. My mouse is being weird. Get rid of that. Get rid of that weird tail. Just to the best of your ability, show that we come here, hit here, and then we do go below, and we do stay below. Make sure it's pretty clear to me that your graph is, in fact, below. But that's it. That's everything. And this was supposed to be blue. Not that super matters. But there's your new graph. It's got two vertical asymptotes, which we hadn't seen before. It's got a horizontal asymptote that we do in fact pass through. It's got some interesting stuff. Hey, let's move on to 5, because we're only on 5 and it's been 40 minutes. Okay, what do you know? You know a lot of stuff. You can see the denominator is x minus 1, so you know there's one vertical asymptote and it's at 1. Wait, do you know that? You better factor first, right? So when you factor, you get x plus 3 and x minus 1. It turns out we do not, in fact, have a vertical asymptote, because these factors of x minus 1 cancel. And what we actually get is a function that doesn't really look like a rational function at all. It just looks like a linear function. It's just a line. But because we have a removable discontinuity at 1, it'll be a line that has a hole in it. But you now, because our function simplified so much, you don't really need to do any more work. You know that you're just going to get a graph that is the graph of x plus 3. So you go up to 3. 1, 2, 3. You'd use your slope of 1 to go rise 1, run 1. And rise 1, run 1. Rise 1, run 1. And then you just sketch the graph. But wait, we do have that hole. And that hole occurs at an x coordinate of 1. Plugging 1 in, 1 plus 3 is 4. So we know that the point 1, 4 is our hole. So make sure you draw me a nice big hole there. But the rest of your graph is literally just a line with a slope of 1. Oh, my eyes are playing tricks. Go, 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 go. There it is. So this is the graph. It's literally just a line with a hole in it. So should you still be answering all these questions here? Of course you should. Definitely got to give me that factored form. But for vertical asymptotes, it's none, because the whole rational function just degraded down to a linear function. So there's no vertical asymptotes, no horizontal, no slant even. There is a hole. We said it was at 1, 4. For x-intercepts, we're passing through the x-axis. If you just drew this well enough, then you can see it's 1, 2, 3, negative 3. If you didn't know that, then, go to your quote-unquote rational expression over here. And the x-intercepts come from the zeros of the numerator. And the only zero of the numerator is then minus 3. So there you go. Your y-intercept is, of course, positive 3. Your y-intercept comes, mx plus b. It's the b value of our line. But there's everything. That's done. Moving on. Well, 6 looks nasty, but it's not. The thing you got to remember here is your numerator, this cubic function, you might be noticing it has 4 terms. And so often when you see 4-termed cubic polynomials, then I hope your brain is saying, let's factor this by grouping. And again, keep the negative attached and just put a plus sign in the middle. Think of this as adding negative x, but don't split the negative off. So let's factor. I'll factor out my GCF. That's x squared, x plus 3. I'll factor out my GCF. My GCF is just a negative 1. So I'll pop that out. That'll leave me with an x plus 3. Now because that x plus 3 is common, I can now factor out the x plus 3. So I can see I'll have a factor of x plus 3. And when I factor that out, I'll only have the x squared left. And I'll only have the minus 1 left. So it'll be x squared plus negative 1. So x squared minus 1. And that means I'm not done factoring yet, because I can factor that difference as squares. So you'll get x plus 3, x plus 1, x minus 1. So there's that thing factored. So that means that this whole function factored is an x plus 3, x plus 1, x minus 1, x minus 1. So this is my factored form. Get those parentheses in there. Denominator doesn't need them. But now this cancels. So my final form is actually x plus 3, x plus 1. Just with the domain restriction, x can't be 1. That means that my beautiful rational function has actually degraded down again to a function that's essentially not rational anymore. It's just quadratic. So you should be expecting to see the graph of a parabola that just has a hole in it, right? So again, I see my y-intercepts are -3, -1, so I can plot those points. -3, -1. I know that at 1 I'll have a hole, so let's take that 1 and plug it in where I can actually evaluate it. So plugging in the 1, 1 plus 3 is 4, 1 plus 1 is 2, so I'm getting a y-coordinate of 8. So my hole is going to be 1, 8. So I can plot that. 1, go up to 8, there's a hole right there. And I'm graphing a parabola, right? So I could actually use symmetry now. I can see that -2 will be my axis of symmetry. So that hole I just found on the other side of this axis of symmetry will be another point. Technically, I guess I should be finding my vertex. So since it's obvious that my vertex is at an x-coordinate of -2, let's just take that -2 and plug that in. -2 plus 3 is 1. -2 plus 1 is -1. So as you may have guessed, we're getting -1. It certainly looks like -1 would have been our vertex. But there it is. This graph is a parabola that has a hole in it. And that's 6. And I'm running out of steam. It's almost 1 o'clock. So we'll probably make this a two-parter. Is 7 particularly interesting? I don't know. I'll do 7. I got gas in the tank for one more. Okay. This one again is looking a little more like a normal one, quote unquote. But this is not going to degrade down to just a line with a hole in it or a parabola with a hole in it, because I can't cancel anything. Now I can factor. I can get x minus 3, x plus 2, all over x. But nothing cancels. And because nothing cancels, I can pretty strongly say that there is no hole. Because the 0 of my denominator is 0, I can say there's a vertical asymptote at x equals 0. Because the numerator has zeros at -2 and 3, I can say that those are my x-intercepts. -2, 0, and 3, 0. My y-intercept, I'm not going to have one, because literally the y-axis is my vertical asymptote. So this is my vertical asymptote. I've got points at -2, 0, and 3, 0. Okay, I can live with that. So what about a horizontal asymptote? Well, I don't have one because the numerator has the greater degree. But it does look like I'm going to have a slant asymptote. So that means we got to do our polynomial long division. I'll try to do it in this space here. We're just dividing x into x squared minus x minus 6. So this should be pretty straightforward math, I would think. X squared divided by x is x, so I get an x. I multiply it through. I only get x squared, so I go to subtract, and I get nothing. But then I would drop down the negative x, and I'd say, how many times does x divide into that? It divides in -1 times. So you multiply, you get x times -1. Did you guys know that? Did you know that you are only multiplying by this term? So don't distribute onto the whole thing and get x squared minus x. Just multiply the -1, and you just get -x, which when you subtract, cancels out again. So drop the -6, but -6 is now just purely remainder. And here's your quotient. This whole thing is now your quotient. This is your divisor. So if I asked you for that quotient equals remainder or quotient plus remainder over divisor form, then you'd give it to me as the x minus 1 plus -6 over x. So maybe instead of saying plus, maybe just say minus. So it'd be x minus 1. And then don't say plus a negative 6 over x, just say minus a 6 over x. But there's our other sort of alternate form. And buried in this alternate form, we see our quotient of x minus 1. That tells us our slant asymptote is the x minus 1, which we could now graph, because we'd go down to negative 1, and we would just show a slope of 1. So rise 1, run 1. Okay, more. So do we cross the slant asymptote? And I know I told you that one way to do this would be to actually take the entire function, the x squared minus x minus 6 over x, and you'd set it equal to the equation of your end behavior asymptote, which is the x minus 1. And then you would solve this. And if there's solutions, then we do cross, and if there's no solutions, then we don't. But I got news for you. That's where this comes in. This remainder bit is another way to tell if you cross your slant asymptote, because once we're in this quotient plus remainder over divisor form, we actually know that if this remainder over divisor term ever equals 0, then that means that you would cross the slant asymptote. Now question, does 6 over x ever actually equal 0? It does not. If I multiplied through by x, I would get 6 equals 0, which is one of them nonsense statements. It's a false statement, so it has no solutions. So I do not expect this graph to pass through. So that's a strong no. And that's good news, because that means I'm done. Because in the first interval, the stuff to the left of this asymptote, I can see that, oh man, that was rough. I can see that all I got to do is come down that asymptote, pass through that point, and then continue down the other slant asymptote, and do the same on the other side. We're going to come running up this vertical asymptote, pass through that x-intercept, and then continue along our end behavior asymptote all the way to infinity. So that's the graph of number 7. 52 minutes is a long time, so I'll do more later. Good night.